All right, in this video, we will be going over section 1.5 in chapter 1. In this section, we will be talking about limit rules and calculating basic limits, okay? So basically, in this section, we are going to learn techniques to calculate limits of various functions, okay? All right, here, first we have this theorem, rules for calculating limits of combinations, okay? So if limit as x approaches to c f of x and limit as x approaches to c g of x exist, then the following rules hold for their combination. Okay, note that we are assuming that these two limits exist. Okay, with that assumption, this we have these rules. Okay, what is the first rule? Constant multiple rule. That means the limit as x approaches to c, k times f of x, this constant times your function f of x. To find the limit of that product, the constant times your function, what you can do is you can take this, pull this k out. Okay, this limit is equal to k times the limit as x approaches to c f of x for any real number k. Okay, simply it tells you that you can pull this constant out and then find the limit. That's it. Okay, and then the sum rule. The limit as x approaches to c f of x plus g of x. Okay, the limit of the sum of this function is sum of the limits. Or in other words, you can kind of distribute this limit as x approaches to c statement. Okay, you can distribute this to this one and this one to get this. Okay, and then a difference rule. Okay, the limit of a difference is the difference of limits. Okay, limit as x approaches to c f of x minus g of x is equal to limit as x approaches to c f of x minus limit x approaches to c g of x. Here also again you can kind of distribute this limit x approaches to c statement inside the parentheses. Okay, and then the product rule. Here is the product rule. If you have a product of two functions and you want to take the limit of that product, limit as x approaches to c, then you can take the limit of each individual function and then multiply them together. Okay. Next, we have the quotient rule. Limit as x approaches to c, f of x divided by g of x is, you can put the limit to the top and the bottom separate. Okay, here we have a quotient, right? So you can take the limit of the numerator and then take the limit of the denominator. And notice that here we require the limit as x approaches to c, g of x is not equal to 0 because your g of x is in the bottom. If this is equal to 0, your denominator is going to be 0, it is undefined. Okay, that's why we require this limit not to be 0. And then composition rule. Okay, remember again, these two limits exist. Okay, limit as x approaches to c, f of g of x, this is the composition of f and g, is equal to f of limit as x approaches to c, g of x, if f is continuous at this point. Okay, or simply what it tells you is that if f is continuous at this limit point, you can send this limit inside. Okay, that's what the last rule tells you. Okay, so let's look at some examples. This is basically the application of these rules. Let's look at this example. Calculate the limits that follow using only continuity of linear and power functions and the limit rules in theorem 1.20. Cite each limit rule that you apply. Okay. All right, let's work on the first part. Maybe I will number these rules. Okay, this is first rule, second rule, third rule, fourth, fifth, sixth. All right, now let's try to calculate the limit. Part A, limit as x approaches to 3, 3x squared minus 2x plus 1. This is equal to, first what I'm going to do is using rule number 1, using rule number 2, pardon me, I can distribute this to the inside, right? So this is going to be equal to limit as x approaches to 3, 3x squared plus limit as x approaches to 3 minus 2x. That's my second term. Notice that my second term is minus 2x. Okay, I take the limit of the first term and then I take the limit of the second term. Here you should have plus sign, of course. And then plus limit as x approaches to 3, 1. My last term is 1. Okay. Now we can calculate these individual limits again. Notice that for the first term, to calculate this limit, using rule 1, using this constant multiple rule, I can pull this constant out. Here the constant is 3. This 3 walks out. Okay. So you get limit 3 times limit as x approaches to 3, x squared. And then again, here I can pull this minus 2 out, which is a constant, using the constant multiple rule. That is minus 2 times limit as x approaches to 3, x. Finally, I have plus limit as x approaches to 3, 1. Okay, I will push this down a little bit. So that's what I have. Okay, all right. Now, how do we go from here? From here, notice that to find the first limit here, this is a power function, right? You know how to find the limit of power function. You just plug in the limit here. Okay, so this will be 3 times 3 squared minus 2 times. Notice that this is the identity function. You can plug in the limit 2 times 3 plus, of course, this is a constant function. The limit of a constant function is that constant. So you get plus 1. To simplify this, you will get okay, so you get 22. Okay. All right, let's work on the next example. By the way, this inequality is by rule 2. Okay, you can simply distribute this limit inside the parentheses. That is coming from rule 2 right here. And then this equality is due to rule 1. It is the constant multiple rule. If you have a constant inside, you can pull that constant out. So that's what I have done here. Here also I have pulled the constant out. Okay, all right, let's look at the next example. How do you find the limit of this one? First of all, notice that this is a composition of two functions. If you take f of x to be x to the power 12 and g of x to be 3x minus 1, then clearly this given function is nothing but f of g of x, right? F of g of x is this given function. Okay, so both of these functions are continuous functions. All right, now how do you find this limit? What rule are we going to use? Remember, we can use the last rule. This is your g of x, right? You can send this limit to the inside function, to g of x. You look at your rule, limit as x approaches to c, f of g of x is equal to f of the limit g of x, limit x approaches to c, g of x. So I can send this limit to inside function. So you get limit x approaches to 1, 3x minus 1, whole thing to the power 12. So you get, what would you get? To find the limit of this function, you can just plug in this limit in the function because it's a linear function, right? Linear functions are continuous. So to find the limit, you plug in the number. Then you get 2, this is 2 to the power 12. Okay, so if you compute, this would be, if you compute 2 to the power 12, this would be 4096. That's the limit. All right, let's move on. Okay, next we have this theorem. Combinations of continuous functions are continuous. Okay, what does that mean? If f and g are continuous at x is equal to c and k is any constant, then the functions k times f, f plus g, f minus g and f times g are also continuous at x is equal to c. Okay, or in other words, if your original function f and g are continuous at x is equal to c, then a constant multiple of f is continuous and the sum of the two functions continuous, the difference of the two functions continuous, the product of the two functions continuous. Okay. Moreover, if g of x is not equal to 0, then f over g is also continuous at x is equal to c. And if f is also continuous at g of c, then f composition g is continuous at x is equal to c. Okay, this is c, by the way. All right, so I'm not going to prove all of these parts, but let's prove one of them. Okay, so what I want to prove is that if f and g are continuous at x is equal to g, x is equal to c, I want to show that this summation f plus g is also continuous at x is equal to c. Let's prove that. Okay, let's assume that f and g are continuous at x is equal to c. When you say f and g are continuous at x is equal to c, what can you say about limits? You can say something about limits, right? What can you say? Limit as x approaches to c, f of x has to be f of c, right? By the definition of the continuity. Okay? If f and g are continuous at c, the limit value should be equal to the function value at that point. Similarly, for the other function, I write it, limit as x approaches to c, g of x is equal to g of c. We have that in our hand. Okay. All right, let's prove that. Prove that f plus g is a continuous function at x is equal to c. How do you prove that? To prove that this is continuous at x is equal to c, we need to show that limit as x approaches to c, f plus g of x, this is g, okay, looks like 9, okay, all right. Limit as x approaches to c, f plus g of x is same as the function value at x is equal to c, or in other words, f plus g of c. How do you prove this? Well, let's play with this one and see whether we can prove it. Okay, so I'm going to play with the left hand side. My left hand side is limit as x approaches to c, f plus g of x. But we know that by the definition of sum of two functions, this is same thing as limit as x approaches to c, f of x plus g of x. That is the definition of sum of two functions. Now what I'm going to do is I'm going to distribute this limit inside the parentheses. That's the rule number 2, right? If you have to take the limit of sum of two functions, you can distribute this limit inside the parentheses. Then you get this is equal to limit as x approaches to c, f of x plus limit as x approaches to c, g of x. But we already know that limit as x approaches to c, f of x is nothing but f of c. F of c, and limit x approaches to c, g of x is g of c. We know that. Okay, this is nothing but by definition of sum of two functions, f plus g of c. It's your pre-calculus. Okay, by definition of summation of two functions, this is f plus g of c. That's what exactly I wanted to show. I wanted to show that this is equal to this. So I simplified my left hand side and showed that I obtained my right hand side. So f plus g is continuous at x is equal to c. F plus g is continuous at x is equal to c. So this completes the proof. All right, let's move on. Next, we have this theorem, theorem 1.22, continuity of algebraic functions. Okay, here is the theorem. All algebraic functions are continuous on their domain. Okay, here is a powerful implication of this theorem, or in other words, we can use this theorem to calculate limits of these algebraic functions. In particular, if x is equal to c is in the domain of an algebraic function f, then we can calculate the limit as x approaches to c f of x by simply evaluating f of c. Okay. This theorem tells you that all algebraic functions are continuous on their domain. That means if you pick a point from the domain of an algebraic function to find the limit as x approaches to that point, f of x, you simply plug in the value in the function. Okay, let's look at some examples. First of all, here are some examples of algebraic functions. Okay, what are the algebraic functions? A function is algebraic if it can be expressed with the use of only arithmetic operations, plus, minus, multiplication, division, and rational constant powers. Here are some examples of algebraic function. Here, as you can see, this is a rational power, and you have x here. This is also an example of an algebraic function. Okay, so here is another example: x plus 1 divided by x plus 2. There are more examples here. Okay, so these are some examples of algebraic functions. Now, suppose you are asked to find the limit as x approaches to 2 x plus 1 over x plus 2. That is the third example that I showed you, this example. Okay. How do you find this limit? Notice that, first of all, this is an algebraic function. From this theorem, we know that all algebraic functions are continuous on its domain. Okay. Notice that this function, this value 2 is in the domain of this function, right? 2 is in the domain. Okay. So that means to find the limit as x approaches to 2 of this function, all what you need to do is you plug in the number 2 in the function. 2 plus 1 divided by 2 plus 2. Okay, this is going to be 3 over 4. Okay. The bottom line is, if you are asked to find the limit of an algebraic function, if that number, the limit number, is in the domain of your algebraic function, to find the limit, you just plug in that number in the algebraic function. Okay. All right. Let's move on. Next, we have this theorem about cancellation of factors, theorem 1.23, the cancellation theorem for limits. Okay, let's see what that tells you. If limit as x approaches to c, g of x exists, and f is a function that is equal to g for all x sufficiently close to c, except possibly at c itself, then the limit as x approaches to c f of x is same as limit as x approaches to c g of x. What does this mean? That means you have two functions. Those two functions are not possibly equal at x is equal to c, but they are equal for sufficiently x for all x sufficiently close to c. Then to find the limit of this function as x approaches to c, that limit is equal to limit as x approaches to c g of x. Okay, let's look at some example. Think about these two. Okay, I'm giving you this example. Let's say x squared minus 1 divided by x minus 1 and x plus 1. Think of this as your f of x. Think of this as your f of x. Think of this as your g of x. What do you think? Would these two functions be equal except at x is equal to 1? Of course, these two functions are equal except at x is equal to 1. Why? This is, if you simplify this function, this is x minus 1 times x plus 1, right? If you factorize the top, in the bottom, of course, you have x minus 1. If x is not equal to 1, you can cancel these two factors, right? But x is equal to 1, you cannot cancel, because if x is equal to 1, this is 0, this is also 0, you have 0 over 0. So it's undefined, okay? But if x is not equal to 1, you can cancel these two factors. What do you get? You get x plus 1, right? It is same thing as your g of x. That means these two functions are the same, except at x is equal to 1. If that is the case, if you want to find the limit of this function as x approaches to 1, you just find the limit of this function as limit x approaches to 1. Okay, as you can see, this is a complicated function. You find the limit of a more simpler function to get the limit. Okay, so this theorem what this theorem simply tells you is that limit as x approaches to 1, x squared minus 1 divided by x minus 1 is same thing as limit as x approaches to 1, x plus 1. Or in other words, you can factorize this top and cancel common factor. You can cancel this factor with this one, and you can take the limit of this one at the end of the day. Okay. All right. That's what it says. Of course, if you find this limit, what would you get? You get 2. Okay. And here you have another example. Let's look at this one. Let's see how to apply the cancellation theorem to get the limit of this. Okay. Well, again, you cancel common factors. That's what cancellation theorem is about. Okay. Limit as x approaches to 1. First of all, notice that you cannot plug in x is equal to 1 as it is. If you plug in x is equal to 1 in the top, you get 0 in the top. And if you plug in 0 here, you get 0 in the bottom. You get 0 divided by 0, 0 divided by 0, which is undefined in mathematics. Okay. So you need to find some sort of a strategies to do this. Okay. So the strategy is that the cancellation look x minus 1, I factorize my bottom. I get x minus 1 times x plus 1, the factors of the denominator. Now you can cancel these two common factors. You have x minus 1 in the top, x minus 1 in the bottom. You get limit as x goes to 1, 1 over x plus 1, which is 1/2. How did I find this limit as x approaches to 1? Notice that this is an algebraic function. Algebraic functions are continuous on its domain. Okay. Notice that this number is in the domain of this function. So I can plug in that number to get the limit. Okay. That's what I did. All right, let's move on. Next, we have the squeeze theorem for limits. Okay. This is one of the most important theorems in this chapter. Let's see what the theorem tells you. Okay. Theorem 1.24, the squeeze theorem for limits. If L of x is less than or equal to f of x less than or equal to u of x. Or in other words, your function f of x is stuck between the function L of x and u of x for all x sufficiently close to c, but not necessarily at x is equal to c. Okay. And if limit as x approaches to c, L of x, and limit as x approaches to c, u of x are both equal to L, then limit as x approaches to c, f of x also should be L. Okay. By the way, similar result holds for limits at infinity and one-sided limits. Okay. We are not going to talk about limit at infinity and one-sided limits here. We are not going to give a proof, but it holds for limits at infinity and one-sided limits. Okay. All right. What does this really tell you? This tells you that if the limit of this function and this function as x approaches to c is equal to L, then the limit of this middle function also should be L. It should be, right? Because this middle function is stuck between these two. If the limits of these two functions are going to L, where can this go? If that is stuck between those two, it has to go to L as well, right? That's the idea. Okay. So, but let's prove this theorem. Okay. So how do you prove? What are we going to assume when we prove this one? We assume that my function f of x is stuck between L of x and u of x. And the limit of this function and this function, they are both equal to L. Then I have to show that the limit of the middle function is also L. Okay. Let's prove this real quick. I copied my theorem over to here again. We need to show that if f of x is stuck between L of x and U of x, and limit of ux and limit of lx are both equal to L, then I want to show that the limit of the middle function is also L. That's what I want to show, okay? So let's start the proof this way. Given, I'm going to start with any given epsilon greater than 0. By the way, I'm going to use the formal definition of limits, okay? Then for any given epsilon greater than 0, since this limit is equal to L, I can write the formal definition for that limit statement, okay? What is the formal definition? For this given epsilon greater than 0, there exists delta 1 greater than 0 such that if my x is in, if my x is in c minus delta 1 comma c union c comma c plus delta 1, then my u of x has to be between L minus epsilon comma L plus epsilon. Why is it true? Because this limit is equal to L. That means for this given epsilon greater than 0, there exists delta 1 such that if x is in this punctured interval, then u of x should fall within L minus epsilon and L plus epsilon. I can write the similar statement for this limit now, because the limit as x approaches to c L of x is equal to L. So there exists delta 2 greater than 0 such that if x is in the punctured interval c minus delta 2 comma c union c comma c plus delta 2, then your function L of x should fall within L minus epsilon comma L plus epsilon. Now I'm going to take my delta to be minimum of delta 1 comma delta 2. If I take my delta to be minimum of delta 1 comma delta 2, what can I say? Then I can say that if x is in this punctured interval union c comma, pardon me, here should be c, union c comma c plus delta, then we should have both u of x, both L of x and u of x between L minus epsilon and L plus epsilon. Okay, that means L of x, I know that L of x is less than or equal to u of x. It's given in the problem. See, L of x is less than or equal to u of x. This is greater than or equal to L minus epsilon. This is less than or equal to L plus epsilon, because both L of x and u of x are between L minus epsilon and L plus epsilon. Okay, so I put this order as well because I know that my L of x is less than or equal to u of x. Okay, now what I can do is I can modify this a little bit further. L minus epsilon less than or equal to L of x less than or equal to, now I am going to place my f of x here because it's given in the problem. F of x is stuck between u of x and L of x, L plus epsilon. What does this tell you? This clearly tells you that f of x is between L minus epsilon and L plus epsilon, right? Why? Because see, L of x is between L minus epsilon and L plus epsilon. That means f of x has to fall in this interval. So that means we have a delta such that if x is in this delta punctured interval, then your f of x is in this interval, L minus epsilon and L plus epsilon. So by definition of limit as x approaches to c, f of x is equal to L. Okay, by definition, we should have limit as x approaches to c, f of x is equal to L. Okay. All right, let's move on. Okay, let's look at an application of squeeze theorem. Use the squeeze theorem to find this particular limit. Okay. You cannot find this limit straight away because you can plug in 0 here, that's fine. But if you plug in 0 here, you have 1 over 0. Okay, 1 over 0 is undefined, right? So we need to have a different way of doing that. What we do is we apply squeeze theorem. Okay, first of all, notice that if I take this piece of function, okay, if I take this piece, I know that this is always between -1 and +1, right? Because the range of sign is always -1 and +1. Okay, so I'm assuming that x is not equal to 0. To apply the squeeze theorem, remember, I don't want to have this inequality at x is equal to c. Okay, here your c is actually 0. Okay, but for all the other values except at x is equal to z, x is equal to 0, I have this inequality. I know that my sine 1 over x is stuck between -1 and 1 because the range of the sine function is always between -1 and 1. Now what I'm going to do is I'm going to multiply this entire inequality by x squared. Okay, assuming that x is not equal to 0. If I multiply the entire inequality by x squared, you get minus x squared here. And then x squared times sine 1 over x less than or equal to x squared. Now view this function as your L of x. That's L of x. View this function as your u of x. And view this function as your f of x. Now you can apply your squeeze theorem. Notice that limit as x approaches to 0, L of x is equal to 0. Also, limit as x approaches to 0, u of x is also 0. Why is that? L of x is minus x squared. Okay, limit as x approaches to 0, minus x squared is 0. You plug in 0 here, you get 0. Similarly, here you get 0. That means by squeeze theorem, we have limit as x approaches to 0, f of x. F of x is this function, x squared times sine 1 over x. X squared times sine 1 over x is equal to 0. Okay, so that is the limit of this function. And you can check using a graph in utility. Okay, try to graph this one, you will see that the limit is approaching to 0. All right, let's move on. Next, we have this definition. This is the way we define the number e. E is an extremely important number in mathematics. Okay, so we define e to be the number that this particular expression approaches as h approaches to 0. That means e is defined to be the number, is defined to be this way: limit as h approaches to 0, 1 plus h to the power 1 over h. Okay, all right. So this is how we define this number e. We will be talking about the importance of the number e later. And then we have this theorem 1.26, this is another characterization of the number E. Okay, the number E satisfy the following limit statement. The limit as h goes to 0, e to the power h minus 1 divided by h is equal to 1. Okay, we can prove this theorem using this definition. We are not going to prove this theorem in this course. Okay, but you need to remember this limit statement. Limit as h approaches to c, h approaches to 0, eh minus 1 divided by h is equal to 1. Okay, next theorem I want to go over is this one, theorem 1.27, continuity of exponential and logarithmic function. Okay, here is the theorem. All exponential and logarithmic functions are continuous on their domains. Okay, so here is an example of an exponential function. Here is an example of a logarithmic function, ln of x. Okay, these are not limited to these functions. Okay, any logarithmic function or any exponential function. For example, this is also an h of x is equal to 2 to the power x. That's also an exponential function. Okay, what this theorem tells you is that all exponential and logarithmic functions are continuous on their domains. What is the importance of this theorem? This theorem is very important in finding limits. Suppose you are asked to find this limit as x approaches to 2 e to the power x. How do you find this limit? You can use this theorem. Using this theorem, by this theorem, you know that the exponential functions are continuous on their domain. Notice that this number is in the domain of this exponential function e to the power x, because the graph of e to the power x looks like this, right? So 2 is in the domain of that function. If that is in the domain of this function, since I know that this function is continuous on its domain, to find this limit, all I have to do is I have to plug in this number in the function. That will immediately give you the limit, e to the power 2. Similarly, in the logarithmic case as well, if you are asked to find limit as x approaches to 5 ln of x, since 5 is in the domain of this logarithmic function, you can plug in 5 to get the limit. Okay, that's what it says. All right, I will prove one of these. I'm not going to prove all. So let's prove that f of x is equal to e to the power x is continuous. For that, I need to show, first of all, this is what I'm going to show. F of x is equal to e to the power x is continuous on minus infinity to plus infinity. Okay, so to show that it's continuous from minus infinity to plus infinity, what I'm going to do is I'm going to pick a point in this interval, minus infinity comma plus infinity. Let's say that point is C, arbitrary point. At that point, I'm going to show this function is continuous. To show that this function is continuous, I'm going to prove that limit as x approaches to C, e to the power x is same as e to the power C. If I can show this statement, it proves that this function is continuous at the chosen point, arbitrary point C. Okay, so this is what I want to prove. So to prove this, I'm going to use a substitution. My substitution is I'm going to take, this is called a change of variable. I'm going to take h is equal to x minus c. That means, this implies x is equal to c plus h, right? I can move this c to the other side. Okay. Then notice that writing limit as, I'm going to write this limit statement purely in terms of h now. That's my goal. Okay. Then if your x is equal to c plus h, writing x approaches to c is same as writing h approaches to 0, right? What happens as h approaches to 0? This will be gone. your x is equal to c, right? That means x approaches to c as h approaches to 0. So instead of writing x approaches to c, I can write my h approaches to 0. That's what I'm going to do. Okay. So limit as x approaches to c, e to the x is same as limit as h approaches to 0, e to the power. Now this is not x, power is not x. My x is c plus h. So I'm going to put this substitution c plus h. Now this is equal to limit h approaches to 0, e to the power c times e to the power h. That's the rule of exponent, right? Now notice that this is a constant. I can pull that constant out. This is equal to limit as h approaches to 0. Oh, I should pull out the constant. This is equal to e to the power c times limit as h approaches to 0, e to the power h. I'm almost done. Remember, I wanted to show that this limit is equal to e to the power c. Okay. So I calculate this limit. It turns out that that limit is equal to this one. Now I'm going to do a small construction. Okay. This is equal to e to the power c. I'm going to rewrite this expression this way. Let me know whether you agree with what I'm writing. Limit h approaches to 0. I'm going to write e to the power h. All right, all what I'm doing is I'm going to rewrite this as e to the power h minus 1 divided by h times h. Then these two will be cancelled, right? Now if I add a 1 to here, this one and this one will also be cancelled. First you cancel these two and then this one and this one will be cancelled. As a result, you get your e to the power h back. Okay. This e to the power h has been rewritten in a different way. Okay. What is the importance of writing this way? Now I can take the limit of this expression and this expression. This is a product, right? So I can take the limit. Then you get, let me copy this one to the other side. Then you get e to the power c times limit as h approaches to 0, e to the power h minus 1 divided by h times limit as h approaches to 0, h plus limit as h approaches to 0, 1. Okay, but notice that this limit is 1 by this theorem. By this theorem, this is 1. And this limit is 0. Limit as h approaches to 0, h is 0. So this whole thing is 0. This limit is 1. So you get e to the power c, okay, as needed. So that means exponential functions are continuous everywhere on their domains. All right, let's move on. Next, trigonometric functions are continuous on their domains. Here, this theorem, we are not going to prove this one. And a strong application of this theorem is we can apply this theorem to find the limits. For example, as x approaches to pi over 2, sine 2x plus pi. If you are asked to find this limit, as you can see, this number is in the domain of this function. So to find the limit, you can straight away plug in this number in the function. Okay? Because we know that all trigonometric functions are continuous on their domains. So that means the limit of this function, limit as x approaches to pi over 2 sine 2x plus pi, is same as the function value at this point, because I know that my function is continuous at this point. Okay, so this would be sine 2 times pi over 2 plus pi. This would be sine 2 pi. Okay, sine 2 pi is 0. All right. Now let's look at some examples. Calculate the limit. This is an easy problem. This is clearly the cancellation row, right? Let's work on these two examples. Limit as x approaches to 2, 2 minus x divided by 4 minus x squared. Okay, as you can see, you cannot straight away plug in the limit, because if you plug in the limit, you get 0 over 0, which is undefined. So that's where the cancellation theorem is going to help us. Limit as x approaches to 2, I'm going to factorize top and bottom. I mean, top I have already factored. It's a linear expression. Nothing can be done. 2 minus x times 2 plus x, the factors of the denominator. Okay. Now, as you can see, you have a cancellation here. 2 minus x is gone. This will be equal to x approaches to 2, 1 over x plus 2, which is, if you plug in 2 in the function, in this algebraic function, you get 1 over 4. Remember, algebraic functions are continuous on their domain. So that's why I can plug in x is equal to 2 to get the limit. All right, next, part B, limit as x approaches to 2. Pardon me, here, this should be limit as x approaches to 0, okay? As you can see, you cannot plug in the limit, this 0 in this function straight away, because you get 0 over 0. So you have to have some sort of a tricks to do that. So the trick is the cancellation law. Not really a trick, the application of cancellation law. So what I'm going to do is I'm going to factorize my top. If I factorize my top, I get e to the power x minus 1 times e to the power x plus 2 divided by e to the power x minus 1. Common factors can be cancelled. Then you get, if you plug in 0, e to the power 0 plus 2, which is 1 plus 2 is equal to 3. Okay, that's the limit. All right, let's move on. The next example is use tables of values to approximate the limit that follow. Okay, we need to find, we need to approximate the limit of this given expression as h approaches to 0. So we do the same trick. What we do is we take sequence of values of h which are approaching to 0 from the right hand side and which are approaching to 0 from the left hand side. Here are the values I'm picking for h. See, I'm approaching to 0 from the left hand side. This is minus 0.1, minus 0.01, minus 0.001. As you can see, they are approaching to 0 from the left hand side. These values are approaching to 0 from the right hand side. Then let's observe what happens to our function value. My function is, of course, this one this time. Okay, so I plug in this h value in my function to calculate the corresponding function value or the y value. Okay, so these are the function values. As you can see, these looks like these values are approaching to some nice number. Look here, these two numbers are very close together, right? They are very close together. This is 2.71. This is also 2.71. That means hopefully from both sides, these functions values are approaching a number. That number is 2.71 to a 2 decimal places. It should be correct to a 2 decimal places. It should be 2.71. Okay. So actually, if you take more and more closer values, for example, if you take minus 0.000001, you will get the value, these two values, to be even closer. Of course, you have to take this one as also to be very close to 0 in that case. Okay. So the value of this would be, I'll give you the approximation. The value of this would be 2.718280 for 6 decimal places. Okay. If you take these values to be very, very close to 0, you will see that it's going to be a number like this. Okay. So this is the approximate value of the number E. Why is this number E? Remember, by this definition, that's the way we define number e. Okay, number e is limit as h approaches to 0, 1 plus h to the power 1. So we have an approximation to the number e. All right, with that, we conclude that section. I will stop there and I'll see you next time.